I hereby open this academic ceremony in which Shenlun Chen will defend the academic thesis using deep learning for quantifying and extracting features from medical images to predict survival outcomes. May I invite you to present a summary of your study and the conclusions of your thesis?
Dear Prorector, dear members of the oppositions, dear friends and colleagues, in the next 15 minutes, I would like to present to you the main findings of my thesis entitled Using Deep Learning for Quantifying and Extracting Features from Medical Images to Predict Survival Outcomes. And firstly, cancer continues to cause a heavy burden on public health. And according to the WHO's reports in 2022, 20 million new cancer cases occurred, and among this, 9.7 million deaths. About 1 in 5 persons get cancer in their lifetime, and about 1 in 9 men and 1 in 12 women die of cancer. And medical images play a crucial role in diagnosis and therapy decision-making. In detail, for the patients who have cancer, and they will firstly get the diagnosis through the image scans, including CT scans and PET scans. CT scans use X-ray to see the tumor inside of patient's body, and the PET scans inject some radioactive materials inside the patient's body to see the metabolism of the tumor. And the physicians will do the tumor staging above mentioned information. And the most widely accepted is TNM stage, where T refers to size and extent of the main tumor, N refers to number of nearby lymph nodes with cancer, and M refers to metastasis. And meanwhile, for patients who get the surgery, and they will have the tumor sections, and these tumor sections will be prepared as pathological slides by some dyes, and the most commonly used is H&E. And these pathological slides will be used for the inspection by the pathologists, and they will do the tumor grading, which means how normal or abnormal cancer cells look under a microscope. And above all, above mentioned information, patients and the physicians will do the therapy decision making. So, however, manual utilization of medical images is quite limited. Firstly, it's caused by the inter-observer variability, which means different physicians can get different conclusions even based on the same medical images. And this procedure is mainly qualitative rather than the quantitative, so it's a very subjective procedure, and the variability of human experts' level of expertise and knowledge not yet recognized by medical science will also cause cognitive limitations, and the laboring and time-consuming is also an important issue. So AI can be a powerful tool to enhance the utilization of medical images. Briefly, AI is using computers to think and learn like humans. And deep learning is a special type of AI just to mimic how the neurons work. And the advantage of AI includes the objective, quantitative, automatic, and fast, and able to find new evidence. So in general, this thesis aims to investigate the application of AI to various medical images. The tasks include predicting survival outcomes and then optimizing decision making. So I will introduce, according to different medical images, including medical image scans and pathological slides. And firstly, it's about the medical image scans. And the first project is AI PCR prediction on CT images for esophageal cancer. And this is a very typical immunotherapy for the esophageal cancer patients. They will get the immunotherapy and get the surgery. And hopefully, they will get the PCR after the surgery, which means no tumor remained inside the body, and so it's good. And if it's not PCR, it's bad. But for patients who get the PCR, they will think that they don't need surgery at all because there are already no tumor inside of their body. But PCR or not can only be known after the surgery is too late. However, our model can predict the probability of getting the PCR before they get the surgery. So if they have the high probability of getting PCR, and the immunotherapy alone may be a good option to avoid the surgery. And the next project is AI DM prediction on CT and PET images for lung cancer. And similarly, patients will get SBRT and have the follow-up. And here, SBRT is a technique of radiotherapy for favorable local control. And the follow-up, including the not distant metastasis or have DM, where DM means is when cancer spreads from its original spots to a different part. It is a very bad outcome because it will cause a very low survival probability for patients. So no DM is good, with DM is bad. So patients who get DM will think that SBRT alone is not a good choice for them. But similarly, it's too late, and our model can predict the probability of getting DM before they get the SBRT. So if the probability of getting DM is high, the SBRT plan needs to be adjusted, and some additional therapies like immunotherapy can be considered. So next is about the application of AI on pathology. For in this study, the colorectal cancer will get surgery after the diagnosis and have the post-operative therapy. And during the procedure of the surgery, we will have the pathological slides, and this pathological slides will be conducted with the tumor grading by pathologists, and this procedure can be realized by AI automation and the quantification. And meanwhile, AI can also do the risk stratification and find some new features that are relevant to the survival outcomes. And these results help us to optimize the post-operative therapy. So firstly, it's the automation and the quantification. So according to the pathological slides, we first develop an AI model to segment the slides into different kinds of tissues. And especially for the epithelium tissue, we use another AI model to segment them into if it's a normal epithelium or epithelium of cancer with a different level of gland formation. And the percentage of the gland formation is actually the results of the tumor grading. So AI can do the same thing as pathologists, and of course, AI is also faster and more quantitative. However, the traditional tumor grading, including manual or AI tumor grading, cannot predict patient survival well. So we developed another AI model based on the segmentation results to predict the probability of survival. And for patients with low or high risk, they are suggested to de-escalate or escalate their therapies. And however, a physician will not satisfied with the results because the results is directly derived for a not TRMPC AI model, so they cannot trust the model. To solve this, we developed a model that's finding and quantifying some new features. And briefly, we use grades with different proportions to see which parts of the pathologic slides have the relevant to the outcomes of the patients. And in detail, our model can tell pathologists that in X location of a Y tissue indicates the probability of survival is increased or decreased by Z. And the results are shown as below, and here is a comparison of the prediction power of different features on the same data sets. As we can see, the AI risk score and the features found by AI reaches a higher prediction power than that of manual or AI tumor grading. And nextly, I will show you how our model can benefit patients. So for patients with stage 2 and 3, after the surgery, they will be grouped into 3 groups with low, medium, and high risks according to their stages, size of tumors, or the number of the lymph nodes. And for the patients with low risk, they do not need any chemotherapy. And for middle risk, need 3 months chemo. And high risk, need 6 months chemo. However, this procedure did not consider the risk come for the pathology. So according to our pathological risk, if for the patients with low risk but have a high risk for pathology, so we suggest them to escalate the therapy. Similarly, for the patients at high risk but low risk for pathology, they are suggested to escalate, de-escalate the therapy. So patients could benefit more based on our new stratifying system. So in conclusion, this thesis represents deep learning approaches for deriving outcomes-relevant features for medical images. And for patients, this is a very typical procedure. They will get imaging scans, per-operative therapy, surgery, post-operative therapy, and follow-up and have outcomes. However, with our AI model, we can know the follow-up before, at an early stage, for example, at the image scans or at the surgery. And we can optimize the therapies at the stage of the per-operative therapy, surgery, or the post-operative therapy. So AI can help us to forecast the outcomes and optimize therapy plan of patients. And however, in this thesis, the limitations include we did not provide concrete evidence to support pathological features, and there is still lacking the explanation in medical image research. So why interpretability is so important? Because it's relevant to the clinical trust, patient care, ethics and regulations, and what's most important is that knowing how things go is the scientific way to know the world. So in the future, firstly, we need prospective trials and biological experiments to provide a more robust evidence, and we need to educate doctors and AI experts on the integration of AI and medicine to give a more high level of the transparency and the interpretability of the AI model. So the joint progress of human and AI is the direction of the future, because only by this we can have a more robust evidence and more interpretable models. So thanks for your attention. I will give back my words to Rector.
Thank you for your presentation. The opposition will be opened by Professor Dr. Axel Sohausen, who was the chair of the assessment committee, and he is chair of our Department of Pathology of Maastricht University. The floor is yours.
Thank you very much, dear candidate. Congratulations. I have to use this one, sorry. Congratulations for your thesis, also very good introduction. I have to admit that I've learned a lot reading your thesis and also in your presentation, and I'd like to extend my compliments to your team of promoters. And basically you said that medical doctors have to be educated. I'm afraid that pathologists have to be educated in the future. But let's see whether this is really true. So basically you introduced us also to the TNM classification in the beginning, which still is one of the most important prognosis predictors which there is, and especially the PTNM, the pathology TNM, which is the basis for this. Although it's not, of course, it is important. But reading your thesis, I just at the beginning, on the first pages, I think it's in the subheading 1.3.1. There's a sentence. The former approach is very popular and the latter approach is emerging in recent years. but to date, computer algorithms driven prognostic predictors have not been accepted in therapy decision making. So they have not been accepted in therapy decision making. You cite a paper from 2017, but since this is a recent one, I think it's still an actual citation. So what is, in your opinion, the reason for this, that it is not accepted in this decision making?
Dear highly esteemed opponent, thanks for your kind question. And for my opinion, firstly, it's caused by the low prediction power of the pathology metrics that we currently use. For example, the tumor grading, or the vascular invasion. Also, in some guidelines, they are suggested to as a high-risk factor to support the decision-making, but there until now, there's not very solid evidence to support this metrics have a strong prediction power with the survival, and including some new some new pathological features like tumor budding or poor differentiation clusters. Something like this is also lacks evidence. And the next reason is that currently the evaluations on the pathology is still too subjective because although maybe according to WHO's guidelines, they will tell you we need to classify the patients with certain cutoffs, like the 15% of the gland formation. However, in the clinical routine, it's hardly be very accurately calculated these percentages. Yes, so the subjective judgment is still take a very important role for pathologist routine. So I think the variability between the pathologists is also a very important issues. And
may I interrupt you? Thank you very much for this very extensive explanation. I completely agree with this, and of course you're right with the tumor budding. This is only important for PT1 stage and for this subset, and it's lots of inter-observer variability. So basically, the point I would like to make is that decision making in cancer treatment is currently mainly based not only of course on the TNM classification whatsoever. And I understand you have some background in oncology. Please ask me if you don't understand what my question is heading to. But the molecular classification is actually currently stratifying the patient treatment. So we have MSI high, we have BRAF, we have KRAS mutations. So, but these are all things which I do not find back in your thesis. I do see a chapter with adjuvant therapy. So I assume, my first question would be, I assume all of the patients you investigated in chapter 2 are non-treated or treatment naive. And what is your opinion on these molecular stratification and your data? How would you bring them together?
Dear highly esteemed opponent, thanks for your questions. Yes, I'm very agreed with your opinion that we should combine the different factors like the MSI with maybe our some you founded the pathological features. This either for the AI model or for the other sources. I think for the respective of the AI research, I think we can use an AI model to fuse these features, including the clinical parameters, because MSI can be considered as some types of the clinical parameters to predict the outcomes. And I also think the MSI is also some format of some imaging data. We can also use some visualization AI model to fuse this different data to predict the outcomes of the patients.
Thank you very much. But are you the group you were testing in colon cancer? Do you know whether they are BRAF mutated or whether they're MSIH or do you have any information about these tumors you used in your study?
Dear highly esteemed opponent, for my project in the chapter 2, we did not include the information of the MSI, and in the research in the project of the chapter 3. And although I did not show this in the version of my thesis, but in the future we plan to combine more features inside to our model. It's also included the MSI, so we will investigate them in the future.
Okay. So maybe a very simple last question. As an old pathologist, I always tell the residents only to look at the. Of course, we do grading. We get a general impression of, let's say, G2 or G1 or whatsoever. But of course, we always name the one component which is the most low graded part of the tumor, let's say G3, there's a certain component of G3 up to a certain percentage. We always name this just to be sure, because this is of biological relevance. Would you find this back in your classification?
Dear highly esteemed opponents, yes, actually our model is developed based on the annotations of the pathologists, and in fact, say delineation on the pathologic slides with some rectangle annotations and tell us if it's G1, G2, or G3. So our models is still based on the annotations of the pathologists. I think so. I think this is quite similar with the real routine of the.
Thank you very much. I'm very happy with your answers. I hand the word back to the pro-rector. Thank you very much.
Thank you. The opposition will be continued by Dr. Shenlun Chen, member of the Assessment Committee and Associate Professor of the Guangdong Academy of Medical Sciences. Please.
Okay, thanks, promoter. Dear candidates, first, I would like to thank for the efforts for the research work in the thesis. It is very interesting. Actually, the work here not only interesting for radiologists, but also interesting for pathologists, right? Actually, in my knowledge, radiology code data and pathological data are often used for diagnosis or treatment monitoring. But in your thesis, your study gave us a new function for survival outcome prediction. That is good. So I have a few questions in your thesis. Could you please read the proposition number 3 and 4?
Interpretability is essential for implementing prognostic deep learning models in decision-making process for cancer patient therapy. And proposition number 4, a balance between interpretability and predictive performance is necessary to enhance the model's utility in clinical practice.
Okay, thanks. For number 3, could you please explain how do you address the challenge about interpretability in your thesis?
Dear esteemed opponent, thanks for your questions. Yes, according to our to my research, especially of the pathology research, we are investigating the compromise of the interpretability and the prediction power of our model. And generally, if we use our more complicated models to predict the outcomes, it will harm the interpretability or the transparency of the model. So to my view, so we should keep some certain principle to firstly, for the prediction outcomes, we should make sure that they have our derived features or the indicators should have the independent prediction power. compared to clinical, the traditional clinical models like the TNM staging system. And for the side of the interpretability, I think we should be more concerned about the interpretability for the physicians rather than the AI experts, because usually the physicians need to link the findings in the AI model to their knowledge backgrounds. Only then they can understand what the visualization or the information model tells to the physicians, and only then we can do some experiments to validate the evidence founded by AI. So this
okay, yeah. Thank you for your question. Yeah, it is another related question about proposition 4. Why it is a balance between interpretability and the predictive performance? How do you understand it? Do you think they're a trade-off, or what you are thinking?
Yes, this conclusion is derived from my own researches, so maybe it have some certain limitations. And for my views, the more complicated models cannot understood by the human experts, and the physician people can even be quite hard to understand some relationship. Maybe it's easy for our AI people. For example, if some factors is relationship should be added, or should be multiplied, should be divided. Sometimes it's not easily to be understood, and if the model is too complicated, the information for the hidden layers can be more difficult to be understood. However, because the technique of the AI is also in the progress, so in the future maybe we will have our and I noticed that the visual transformer model is become more and more popular. So the combination of the attention mechanics and the traditional visualization AI model can help us to understand the model better. So maybe in the future we can solve this dilemma.
Okay, yeah, thank you. Now question is about in page 11, the figure 2. What do you mean about the black line from machine learning to traditional machine learning? Because I can see the red line and the blue line, right? One is for, it means that the method is popular, and another one is the method is not popular. But what do you mean the black one, the black line?
Dear esteemed opponents, I want to check that if you mean the black box.
No, not that. In page 11, there is a figure 2. Yeah.
Sorry, wait for a moment.
Yeah. There is a figure 2.
Okay.
In the figure, you mentioned, three colors. One is black, red, and blue. In the right bottom box, you only mentioned the red and blue line. What do you mean the black one? Especially from machine learning, traditional machine learning.
Thanks for your question. And yes, here I classify the deep learning model into some traditional machine learning model, and to be honest, it's quite simple because the traditional model is about some traditional machine learning model like like KNN, something like for random forest. And or even XGBoost, this traditional algorithm, and compare with them is the deep learning model, because deep learning model usually involves higher amounts of the parameters and are more complicated models and with maybe lower interpretabilities. So this is my classification of the traditional or the.
But why it is not popular using deep learning in the prognostic task? But you mentioned that it is very popular. It is widely used in diagnostic task.
Dear esteemed opponent, and I think for the diagnostic tasks, I think we need more simple models because we have something like a very clear stage in the middle, like the T stage or N stage, or maybe it's just contouring something. So I think the model usually maybe the simple model, if it performs well, it will be a good option. So, and according to my investigations, I found that for some diagnostic models, the traditional machine learning maybe it's a better options rather than using a very complicated deep learning model to fix a simple task.
Okay, yeah, clear. Yeah, my next question is about.
Can you make a short question and a short answer?
Yeah. In the same page 12. For the first question you want to address in your thesis, have you already found the answer? Very shortly question.
Sorry, dear esteemed opponent, I'm quite understand your questions. I cannot hear very clear. Sorry.
In page 12, you have 4 questions you want to address in the thesis.
Sorry, I did not see. I did not see this in my page 5. Sorry. Oh, to 12. Sorry. Oh, okay.
Okay, 12. For the first one, have you already got the answer? Because you mentioned that you.
Okay. So sorry. I found the wrong page.
On it.
What's the future? Yes. Just as I will reply very simply. Just like my work in the chapter 3, I think keep the interpretability and the prediction power is the future orientation of the work.
Okay. Thank you.
Okay, thank you. So the opposition will be continued by the member of the assessment committee, Professor Regina Beets-Tan of Maastricht University of the Department of Radiology.
Thank you very much, Professor. Just want to check, do you hear me well? Because there was a technical, yeah? Okay. So very much congratulations to the candidates, but also the supervising committee for this excellent thesis. I have read it with much pleasure. I am a radiologist. If you have visited radiology congresses, it's like the most popular is the AI exhibition and sessions, but I didn't know a lot about the pathology. So I would like to focus on pathology and not on your imaging chapter. So my first, I want to delve deeper into what you were saying, your answer to the clinical application. I still do not get very well the real world barriers of translating your model into the clinics. Can you explain it a little bit more clear? And then with respect to the workflow integration and the cost, but also the buy-in from clinicians. Do more, can you convince me?
Dear highly esteemed opponent, yes, I'm very willing to share some of my opinions, and I can share you the some of my experiments during I'm doing the projects about medical imaging data, because in that model I use AI model to derive the features for the GTV, and then reconstructed the GTV based on these features. So in this procedure, yes, we'll have a very interesting issue is that we use less features to present the features, and how many of the features are enough to percentage the structures of GTVs. So in that procedure, I tuning the numbers of the features from high to low, and I will let the physicians to check the reconstructed GTVs at every time. When I found the exact numbers that the patients, the physicians can still consider that the reconstructed GTV have the values of the diagnosis, and when I furthermore reduce the features, and they will lose, the GTV will lose the shape, and physicians cannot think it still have the diagnostic values, so I will choose the right numbers or of the deep features to represent the structures of the GTV. I think this practice is, for me, is quite a good example to cooperate with the physicians and AI experts. So for our AI experts, we should always introduce some basic AI conceptions, and continues to provide the visualization things to physicians, and make us, we can understand each other, and we can do the all work better. Okay.
Yeah. Okay. Thank you very much. But a very, very detailed explanation. But I wasn't referring to the imaging. But I was very much wondering about the pathology. So my question is, in pathology, you need a substantial pathology infrastructure. And there is a lot of money involved in that. It's not easy. It's not, it's expensive. And we are in the attempt to use AI as an assistance is to also generalize the healthcare, so the diagnostic pathology, in countries with lower resources, with lower income. So what is your vision of how we implement the pathology scores into the clinical workflow? That was in fact my question.
Okay. Thank you. Thanks for your question. And currently, our pathological models, the AI application can firstly give the results of the tumor grading, and usually it's maybe quite laboring for the pathologists, so it can save the time of the pathologists, and we can also quantify a lot of other tissues that usually be very hard to quantify, like some lymph nodes, and the environments of the tumor under the pathological slides. And sometimes, although I did not mention this in my thesis, but we also have the application of the AI on the H&E stand slides to transform it into some maybe quite expensive and laboring IHC slides. so it can also save money. So I think there's two aspects. The firstly is the prediction model can help us to let the pathology factors plays a more important role in the decision making, and secondly, it can help us to solve a lot of labeling things and quantifying some new interesting things to find the relevant in the future. It can save time and money.
Yeah, I agree. Just one last question. Is that okay?
Yes.
Okay. So I was wondering, you are using training the data, and you're using the Cancer Genome Atlas data. But then the validation was from one single institution. So how confident are you that your model can be generalized across the different populations? How can you ensure that the model is robust and can be performed in different clinical settings and environments? So what is your thought about that? And if it's difficult, what would your strategy be to make that happen?
Dear highly esteemed opponent, thanks for your kind of question. And to my view, I think I think sorry, I'm quite forgot your questions.
How can you generalize your model into different settings, because you only validated it in one single center institution?
Yes, I think the diversity of different institutions and the patients exist. So so maybe it's a good option to do the fine tuning for each institutions. However, as you just said, that the general use of the model is also very important. So I think maybe in the future we can do the federated learning at a very large scale with different institutions with different characteristics of patients for different countries to build a quite a general model. Maybe this performance is not good as some local models, but it can help us to reveal some more important evidence. And yes, and for the real usage, we can still do the fine tuning based on this big model. Okay.
Yeah, I fully agree with that federated learning, and that's why in the imaging world we are already building such an infrastructure. So yeah, thank you very much. I'm satisfied with the answers, and I would like to give back the floor to the pro-rector.
Thank you. The opposition will be continued by Dr. Samuel Luck, Assistant Professor of Boston University, Department of Radiation Oncology and Artificial Intelligence.
So thank you, Pro-rector, and congratulations to the candidate and the supervising team for the great work. I think this predicting model will be the future of a lot of clinical practice and potentially should be in a clinical trial maybe today. So I want to focus more on chapter 6 on the application of on SBRT lung with distant mass or not. So the first question is, you mentioned a lot about how does the image or your deep learning model and your other clinical parameters affecting the outcome or with or without distant metastasis. How about, do you observe anything relating to the radiation therapy parameters, like those, like the technique or the machine they use type of thing?
Dear esteemed opponent, yes, thanks for your questions. Yes, I think your question is very valuable for these works. We designed these experiments because we fix the same therapies of the patients, which is SBRT, to investigate the response to the therapy of the SBRT, so we can adjust the SBRT. But I think for every different features, for every different patients, of course they get different therapy, especially radiotherapy plans. So the dose distributions and their effects, that's nearing the tumors or inside the tumors, are quite different, and they receive the different dose delivery. So I think in the futures we can also include the dose maps of these patients as also an input of our deep learning model to realize a more personalized prediction of outcomes. And I think this model can have a higher prediction power and can also be very helpful for our personalized therapy.
Thanks for the answer. I totally agree on this dose map and potentially acting like patient risk or tumors, like from your other pathology study, like the tumor staging, other pathology features could be combined to predict the patient outcome on this as well. So do you use, my second question is, in both chapter 5 and chapter 6, you use the variation autoencoder to extract features from the CT and PET imaging. Why do you choose this over like other potential model to extract features? What's the advantage or disadvantage of using variation autoencoder?
Dear esteemed opponents, I want to check if your question is about why I choose the model of firstly you use the VAE model to extract the features and you then use these extracted features to predict the outcomes. Is my understanding correct?
My question is more on. You are correct on the first part. I'm wondering, so there are a lot of other potential like feature extraction algorithm from images. Why did you choose VAE?
Yes, I understand that there are other algorithm. I choose VAE because it can be reconstructed to make sure that physicians can check the diagnostic values of the GTV, so we can make sure that our extracted features still hold the main structures of the GTV. It's not checked by some metrics, but the judgment of the human experts. So the projects can be derived into two parts. And when we confirm that in the stage 2, our extracted features are good, and then we can use these features to do the further research. This is my consideration.
Do you mean that the extracted features are somehow interpretable in this case, that the radiologist can understand?
Sorry?
Let me repeat. Do you mean the features extracted from the VAE are interpretable so that the radiologist can understand and determine if it's good features or not?
Yes, I think the radiologist cannot understand the features directly, but they can understand the reconstructed GTV masks based on these features.
Okay, I get it. Thanks. One more question. So, in your study, you use a C index as an assessment to the model predictive power. Do you think it's a suitable performance indicator? Say, if I am a clinician, I want to find an AI model to help me to determine if a patient should get adjuvant chemotherapy. Say, I want to have a clinical trial. Is this a suitable parameter that I can tell this is a good AI model? If yes, what is a good number I should consider? If not, or what other parameters I should consider?
Thank you, dear esteemed opponent. Yes, sir. Usually we use CC index as a matrix because it's quite stable and easy for our understanding, but it's statistically it's obviously not cannot be easily understood, especially for the patients. So I think. So actually, our predicted is partial hazard ratios of the patients, which can be somewhat considered as a risk score, and this risk score itself cannot be used for the decision making. So it's still need to be seen in the real data sets if the patients have some at a certain degree of the risk stratification. So I think your question is maybe it's more about the shared decision making between the doctors and the patients. We should expand the patients that you maybe have a higher or lower risk, so maybe we suggest you to escalate or de-escalate the therapy, and this decision can only be made both of the opinion of the patients and the physician. So I think it's a very complicated question, so I cannot answer you directly which parameters is better than C-index in our real clinical usage.
Okay, will get.
Thank you.
You will get time to continue that discussion. Don't worry about that in the protocol. So the opposition will be continued by Professor Dr. Engineer Matti Leers from the Open University Zuiderland, and with expertise on data-driven decision-making in healthcare. Please.
Thank you, Mr. Prorector. Dear candidate, first of all, I would like to congratulate you about the work, but also the supervisor team, and especially about the use of deep learning to investigate medical images. It's great work. My questions will be pointed to the chapter 2, 3, and 4 about the whole slide images. And especially about the impact of whole slide images on the performance of an automated system. In practice, colorectal tumors are often too large to be fully captured into a whole slide image. So a whole slide image typically represent only a portion of the tumor. And this partial view usually starts at the from the still healthy colorectal tissue, going to the border of the tumor to the center. Additionally, we also know that tumors are highly heterogeneous, with some regions showing poorly differentiated tumor glands, but also regions with well differentiated tubular glands. And next to that, we also know that there are multiple clones of tumors within a tumor. Knowing that, how do you correct for that in your artificial intelligence model when you use that?
Yes, dear highly esteemed opponents, thanks for your questions. Yes, exactly. It's a very important questions for our research about use whole slide images. Usually, the pathologists will choose the parts that they think is most representative to make the whole slide images. However, of course, it still have some limitations. It's only after all, it's only a part of tumors. So. But for the evaluation of the pathology and our AI model, we can only use such kinds of data. So yes, so I admit that this is a compromise of the current study, but it's it's quite it's a very complicated the issue to be solved. So in the future, I think if it's possible, we can let the pathologists to segment the more whole slide images for the tumor sections with at the different spots, so maybe it can solve this issue partly.
Okay, I have a very small related question about it. Is that in chapter 4 you combine hematoxylin azine stained section with immunohistochemical stained section.
Yes.
You use the CD31, you use HIF1 alpha, and there's another one I forgot at the moment. But each section is roughly 4 micrometer thick. So between the first hematoxylin azine stained section and the last immunohistochemical stained section, there will be a depth of 20 micrometer. So knowing that, certain tissue boundaries may shift slightly and affecting the appearance of specific cell structure. For example, small vessels, which you stain with CD31, will be at other place than the original hematoxylin azine stained section. How do you correct for that?
Dear highly esteemed opponent, yes, in the research of the chapter 4, we only use IHCC slides, and we use annotations that pathologists directly do the delineation on the IHCC slides. Although it's not often the practice, but yes, but they just simply classify the tissues into tumor or non-tumor. But your questions do exist in our future works because we need to registration the H&E and the IHCC slides. So currently, we have 2 approaches to solve this. And the first is let pathologists to cut the slides as close as possible so we can consider it's approximately the same place. And secondly, we can also use some AI models to do the registrations of the HE and IHC.
Thank you. Thank you. I give the floor back to the provider.
Yeah, thank you. So the opposition will be continued by Professor Dr. Anna Wiebig of Maastricht University, and her expertise is data fusion and intelligent interaction.
Thank you, Mr. Prorector. Esteemed doctoral candidate, I compliment you with the good work, especially the extensive experimentation with many data sets. Despite this good impression your work makes, I'm still left with some questions that I want to discuss with you. And the first question is related to the proposition number 6. So if one of the paranymphs can read it.
With 4 parameters, I can fit an elephant, and with 5, I can make him wiggle his trunk. Von Neumann.
So in your thesis, the data sets that you are using are relatively small. In most chapters, less than 1,000 data samples. Yet the models that you are using, they are big. They have many parameters. Don't you overfit the models?
Dear highly esteemed opponent, yes, of course, I think my model will be at risk of some certain levels or overfitting. So this is why we need to do some prospective trials or some do the real validations through some experiments to validate the findings and our new models. And also, to my view, as a proportion of the 6, I mean, too many parameters can be at risk of the overfitting, but it can also reach some answer we cannot answer before. So I think our approach is to find the clues of this very complicated parameters and simplify the hypermeters and convert to some scientific evidence we can understand and validate it. I think this is my opinion.
Okay, thank you. In chapter 3, you use expert annotations. What is, in your opinion, the best strategy to manually annotate the data set? Let's say we have 10,000 data samples and 5 experts. So what would you do? What would be your advice?
Dear highly esteemed opponents, thanks for your questions. Yeah, I have to admit that sometimes it's a very laboring work for the annotations. To my view, we can solve this just by firstly, we train the model on some less numbers of the samples and train a model and do the first the delineation, AI delineation, and then the AI, human experts can modify the AI delineation and then feed back to AI again. I think modifying the AI contouring is much more easier than contouring is simple again. And of course, using some unsupervised model is also an option.
Thank you.
Shenlun Chen, the time appointed for defending your thesis has passed. The degree committee now will withdraw to discuss the quality of your thesis and your defense. I request that you and your company await the results of our deliberations and of our return in this room. Close.
The PhD defense has now ended. The degree committee will debate the candidate's performance behind closed doors. This process usually takes about 10 minutes.
Long road to the south side. 7 miles in my rearview mirror, I know what it felt like. My goal's only getting clearer, east side to the west side. No place like home, if it's questions that you've got, go the extra mile and die. All your time, cause I'll go the extra mile. Long road to the south side, 7 miles in my rearview mirror, I know what it felt like. My goal's only getting clearer, east side to the west side. No place like home, if it's questions that you've got, go the extra mile and die. On the dash, got my laces tied. Long road, I don't waste no time. Break rules because fate decides. With the team and we chase the light. I make a move, fall down, shake it off. I hate to lose, bad branch, break it off. No room for negativity, praise and love. Prepare for deep part cause we're taking off. Take the mileage, traveling so far from home. Gathering knowledge, other connections. I put the time in to get everything I ever hoped for. It's a challenge and we all in. It's a better future that we go for. Even though these nights seem long, I know that I am never on my own. Know you won the battle once you grow. South side, 10 miles in my rearview mirror, I know what it felt like. My goal's only getting clearer, east side to the west side. No place like home, if it's questions that you've got, go the extra mile and die. Long road to the south side, 10 miles in my rearview mirror, I know what it felt like. My goal's only getting clearer, mirror, east side to the west side. No place like home. If it's questions that you've got, go the extra mile or die. What's on the line? I know you know that I can't read your mind. Years can't fly by now, don't waste all your time. 'Cause I'll go the extra mile.
decided to grant you the degree of doctor. And Professor Dekker is authorized to confer upon you this academic distinction in accordance with the Dutch university custom. I invite your supervisor to now take the floor.
First, you have to make us a promise. Do you promise to work in accordance with the principle of scientific integrity at all times, to be careful and honest, transparent, independent, and responsible?
Yes, I promise.
Then, by the authority vested in us by law and in conformity with the decision of the committee here present, I hereby confer upon you, Shenlun Chen, the degree of doctor, and grant you all rights attached by custom and law. As evidence of this, I now present you with the degree certificate signed by the rector, the secretary and the other members of the committee, and affixed with the official seal of our university.
Dear Shenlun, today we gather to celebrate a remarkable academic achievement for you, and even more, a more remarkable individual. It has been my great pleasure to be a co-promoter of you, who today stands at the finish line of a challenging, transformative journey. Along the way, you have shown not only as a dedicated scholar, but also as an accomplished gamer, a history enthusiast, and most importantly, a good chef. From day one, Shenlun brought a unique flair to his PhD journey. While most students juggle research and study, he somehow found the time to master the art of Chinese cuisine and even sushi. Trust me, his cooking skills could compete with any restaurant, and when he gets into sushi mode, the precision he applied could rival the most exciting standards of clinical data science. Just as he understands the application of deep learning as a clinical data scientist, he understands the perfect balance of flavors in soya sauce and ginger. Of course, not only does he cook delightful dishes, but he also cooks up a storm in the gaming world. Many of you may not know this, but he's an incredibly skilled gamer. He can calculate complex dose distribution in nutrition planning in 1 minute, and then pick up a controller next and enter virtual battles with the same precision as he applies in his research. I've heard also, though I cannot confirm, how many late nights might have been spent on just one more game. And who could forget his email address? I've seen yesterday your initial application for a PhD, and I've seen that part of your email address was included the name of one of the fathers of quantum physics, Schrödinger. It's a perfect email for a physicist, though I'll admit that I often wonder, are his messages in that inbox both read and unread at the same time? But just like Schrödinger's cat, I figured it was best not to look too deeply in that mystery. Behind the lab and his virtual world, Shenlun has a deep appreciation for the European history, and particularly its fascinating layers of culture and politics. Conversations with him could easily drift from the dynamics of proton therapy to stories of dynasties and historic events that shaped nations. So, here's to you, Shenlun, Dr. Shenlun Chen. May your future be filled with success, endless rounds of sushi, and perhaps a few new historical eras to explore. Congratulations, Doctor.
Dear Dr. Chen, Also, on behalf of the Maastricht University, I congratulate you with the degree you have acquired. And now I close, and before I close the ceremony, I just have to inform you that we make a small photo here, and then at the stairs, and then you have time to congratulate the doctor. Close.
Let me also take the opportunity that unlike other PhD defenses, there is no reception here, but we go immediately to Café Zuid, which all of you are invited to, and you should know when you look at your calendar where it is.